I'd like to bring this back to the program. I think everybody had a great breakfast, and could we recognize our wait staff for the superior job that they have done? Today is an important day in history, and I'd like to take this time to recognize any veterans that there are in the audience. Could you please stand and be recognized, and we appreciate your service. Thank you so much. AMATYC appreciates the support we continue to receive from our publishing companies. 2 publishers have shown their exceptional support by becoming AMATYC corporate partners. And we do have representatives from both of our corporate partners here with us today, and they are going to bring us greetings. First is Hawks Learning Systems, represented here by my good friend, Abby McBride, their National Sales Manager.
Good morning, everyone. That was excellent. My name is Abby McBride, and I am with Hawks Learning. And this year is a special one for me. It happens to be my 10th AMATYC conference. Thank you. And, each year, it never ceases to impress me at what a fantastic effort goes into and really job is done by everyone that puts together this annual meeting for us. So I was hoping to start by asking that you all join me in recognition of the members of the AMATYC board, our conference committee members, our regional hosts, and really all involved in making this event possible. So thank you so much for all that you do. And at Hawks, we really feel privileged to have the opportunity to work with and learn from each and every one of you at not only this meeting, but throughout the entire year. We're proud to be celebrating our 13th year as corporate sponsors of the AMATYC organization this year. And I had a conversation last night that really inspired me with who I'll now refer to as the legendary Ernie Danforth. Oh, wow. And his words really stayed with me. So I wanted to share a little bit with you about what he had to say. He said to me that AMATYC is a people organization, that it's about the people that come here to collaborate together and that care so deeply about the people and touching the lives that you touch in your classrooms each and every day. And I truly feel that what everyone in this room does on a daily basis has a very real and tangible impact on our future. It's an inspiring opportunity to me to be a part of an educational community that is constantly striving to improve and seek better ways to reach our students. It's often said that one of the only constants in life is change. And I firmly believe that the importance of and really need for educators that are passionate about their mission to play a role in a better tomorrow and to positively affect the lives of the learners that come to your institutions is certainly another. So thank you for all that you do and the opportunity to collaborate with you. I hope that you leave this conference, as we do, invigorated and inspired. And please continue to expect more and to share ways in which we can better serve you. It certainly is our mission at Hawks to continue to support yours and your students in any way that we possibly can. So thank you again, and I hope to see everyone next year in Orlando. Thank you.
Thanks, Abby. And now our second corporate sponsor is McGraw-Hill Education. I would like to introduce their representative, their managing director, Kathleen McMahon. Kathleen?
Good morning. I am so pleased to be here with you all. This is my first AMATYC. Thank you. Thank you. I'm no stranger to education. My background is education. I was a classroom teacher myself for 6 years, and know the journey that you all are on very well in working with students and improving education. I've been in the publishing industry for 15 years, spent the last 10 in the computing discipline. So I'm thrilled to be here in working with you all in the math education discipline. So I've been incredibly impressed with this event. I think that the AMATYC, the association, and the executive board have done a fantastic job with this event. I've appreciated getting to know some of you this week. McGraw-Hill held about 15 focus groups over the last 2 days and got a lot of really great feedback from you all that we're gonna take back and apply to the products that we develop. So I wanna thank AMATYC for the continued partnership. We are very much invested in and passionate about improving math education and partnering with this association, faculty, and students to do so. We believe that it starts with placing students in the right courses and then giving them the tools and the learning experiences through their coursework to get to graduation and find success in their careers, both STEM and non-STEM. This journey that we're all on together to motivate students to be confident, lifelong learners is filled with challenges. And we are dedicated to partnering with you to solve those challenges through the products that we develop, like ALEX. So thank you for allowing us to be here and support you and be a part of this journey. We very much appreciate it, and we thank the association for this opportunity to bring the math education community together. We look forward to joining you all in Orlando next year once again. So thank you very much. Thank you.
Thank you to both Hawks and McGraw-Hill Education. We do really appreciate your support. It is now my pleasure to introduce the 2016-2017 Executive Board for AMATYC. Please hold your applause until all of the introductions have taken place. We have President-elect Jim Ham and past President Nancy Sattler. David Tanner is the, please stand, David Tanner is the treasurer, Michelle Duda the secretary. The regional vice presidents are Ernie Danforth, Northeast, Dan Farnger, Mid-Atlantic region, personal joke there. Nancy Rivers, Southeast vice president. The John Oakes, Midwest region. Nicole Lang, Central Region. Oh, back. Kate Kozak, Southwest Region. There she is. Liz Hilton, Northwest Region. Mark Harbison, West Region. And Cheryl Cleaves, AMATYC's Interim Executive Director. Please welcome, recognize them with a round of applause. They're the ones that make me look good. So I can't express all that you have done for me and for AMATYC. Would all of the affiliate presidents that are out there please stand and be recognized? There's got to be some of you out there. We thank you for all that you do for promoting AMATYC within your affiliates, and together we will be strong in the voice of mathematics taught during the first 2 years of college. On Thursday, during the Affiliate President's Luncheon, a name was drawn to receive a Presidential Student Scholarship. I would like to announce that the recipient is Alexandra Glaskowski from Genesee Community College in New York. So thank you for that. And you'll notice that I said that this was a recipient of the Presidential Student Scholarship. At the board meeting, we have renamed this scholarship to the Wanda Garner Presidential Student Scholarship. So if your affiliate did not submit a name this year to be considered for this scholarship, please be sure to do so next year. Information can be found on AMATYC's website for all the information that you need to know how to recommend a student for this. I also would like to introduce to you the academic committee chairs. Again, if you're here, please stand up, and I will recognize you all with a round of applause at the end of the committee chairs and the ANet leaders. We have Paula Wilhite, Developmental Mathematics, Dan Petrick, Innovative Teaching and Learning, Stefan Barato, Mathematics and its Application for Careers, Scott Peterson, Math Intensive, Banaz Farhani, Placement and Assessment, John Smith, Research in Mathematics Education in the first for two-year colleges, Julie Hansen, Statistics, Andy Jones, Teacher Preparation. Let's give them a round of applause now. We also have our AMATYC networks, affectionately known as ANet leaders. We have Christine Merbaha, Division Department Leadership, Steve Kravitsky, Interventional Mathematics, Judy King, Adjunct Faculty Issues, and Ferry Sammy, Mathematics for Liberal Arts. Let's give them a round of applause. The AMATYC office staff are responsible for the day-to-day operations of the organization. They are, and there's a lovely picture of them, Christine Schott, Publications Director, Beverly Vance, Office Director, Christy Hunsaker, the Accounting Director, and Linda Ragland, Technical Clerk. Let's give them a huge round of applause. I'm doing something different. I tend to do things differently, right? I just want to recognize, you guys have been a great source of inspiration to me. Your leadership in the past helps me in the future. My executive board, I've already said some really great things about you. You are the best, even though my pillows tend to show up missing, but we won't go there. The office staff. We've had a hard couple of years. You have been there for us. You make us look good. And I want to present the office staff with a Herb Gross Presidential Award. All of you have meant the world to me, and I have plaques for you. Please recognize the office. You may caught on that they did not know this was happening. There were 3 people who knew. Well, no, we have to add, we talked about back there a little bit. Wanda knows, and she is here because we had this plan for this long. And Cheryl took over Wanda's role in the surprise, and words can't express all that you have done for the organization, for many of you for over 20 years. And you bring the organization forward, and it is time that we recognize you for all that you do. So again, thank you so much. And next, we have the Student Math League is in the capable hands of coordinator Steve Hundert and test developer TJ Duda. Would both Steve and TJ come on stage? And they are going to present the Charles D. Miller Scholarship.
Morning. So last year's AMATYC Student Math League competition involved over 12,000 students at 168 schools, including one in Guam. And no, I didn't run it alone. This is truly a team effort. So I want to thank Pearson Education for generously funding our grand prize, a $3,000 scholarship. Mu Alpha Theta for providing copies of Mathematica to our top 10 players, and Association for Women in Math for providing membership to our top 10 women. Also need to thank TJ Duda and its Test Development Committee for providing both the questions and the answers to the competition. I want to thank George Hobart for maintaining the website and the electronic scoreboard, and of course Beverly Vance and Christine Schott in the AMATYC office for way too many things to mention. And of course, a big thank you to all the moderators and other faculty who recruit our players. we get the moderators to stand up, get a round of applause? There's a lot not there. So they're the ones that do the lion's share of the work. They recruit the players, they run practices, administer the tests, grade the tests, and post the scores. This league would not exist without everyone's effort. Many awards were given out at the Friday regional breakfast, but we saved the best two for last. We'll do them here today. For the third year in a row, the first place team is West Valley College from California. Accepting the award is Rebecca Wong. And this year's grand prize, the Charles Miller Memorial Scholarship, goes to Shengjiang Zhou Yo, better known as Stephen, from Fullerton College. Also in California. Accepting the award for Stephen is Mark Greenhoff. Stephen, interestingly, will be using his scholarship to attend UC in San Diego. All right, enough with the kid stuff. On to the pros, which can only mean the Steve Blasberg Faculty Math League, where once again the plexiglass, much coveted plexiglass trophy is up for grabs, along with individual awards, a $100 Amazon gift card generously funded by Mu Alpha Theta. And Steve's here to announce the winners.
So the individual winners, the top three, as we always do, are third place was Sean Saunders from Sheridan College, and if that college is unfamiliar to those of you who are not in the Northeast, it's in Oakville, Ontario. Second place from Middlesex Community College, also in the Northeast region, is Aisha Arroyo. And first place from City College of San Francisco, yes, in California, is Michael Greenberg, who got an astounding score of 33.5. For those of you who know how the grading is done, that means that he got 17 right out of 18 problems, which I think is the best ever. All three of them will be receiving gift cards from us in the mail. And now to the big winner. The winner for the regional trophy is, as you might have suspected, since they got 2 out of the top 3, is the Northeast region with a total score of 85.
Can I photo that? Wait, we've had a request here.
I promised this to my region if they ever did this. We are the champions. We are the champions. We are the champions of the world.
In case you couldn't tell, I'm from the Northeast. I was once a very happy vice president, like Ernie is right now. But thank you for Steve, TJ, and Steve for all the work you do with the student and faculty math leagues. It's been a fun competition among the regional vice presidents for years, so thank you. Continue along with the recognitions. We have Peter Georgakis, the legal advisor, Wendy Morrison, the editing director, Lisa Feynman, the historian, also Paige Perry, the representative to Mu Alpha Theta, and Dennis Ebersol, the grants coordinator. Could we give them a round of applause? Our publications area, we have Diane Koenig, the AMATYC News editor, George Herbert, the website coordinator. You guys are standing, right? George Alexander, our editor, Johanna Debrecht, our production manager. Let's give them a round of applause. Our professional development coordinator is Julie Gunkelman. Julie is over here. Thank her. She's great. How many of you have been on a webinar or watched a webinar? She is the face of AMATYC, and she does a wonderful job. So thank you, Julie. In addition to the AMATYC board members who serve on the foundation board, 4 individuals round out the foundation board. They are Fred Peskoff, Rachel Black, Cheryl Cleaves, and Bill Stinken. So please welcome them with a round of applause as well. AMATYC has an investment committee that consists of 2 AMATYC board members as well as 3 additional members serving on the investment committee, and they are Bill Stinken, Wilson Grubb, and Phil Mailer. We could recognize them. This one's going to be a popular one. Christy Hediger, she is our project access coordinator. Will all of the fellows, both past and present, please stand and be recognized? Look at the room. Fantastic. This did not look like this when I sent it, but it did look better when I set it up. AMATYC has 24 past presidents, and many of them are attending this conference. Will all of the AMATYC past presidents, it's supposed to look like that, will all of the AMATYC past presidents please stand and be recognized? On behalf of AMATYC, I thank you for your service to the organization. The conference planning team is led by Kevin Doctor, the conference coordinator, and he is assisted by Honey Kirk. You guys don't listen well. Thank you for everything. We have Natalie Vega Rhodes as our advertising chair. Jay Martin is our exhibits chair. Darlene Whittington, I was going to do all. Darlene Whittington is our presider chair, and Sarah Miller is our roommate network director. If we could recognize them. Our conference program committee, our program coordinator is Judy Williams, and she is part of the conference planning team as well. And Judy is assisted this year by the conference program committee. Those people on that committee are Chris Algier, Jeffrey Berg, if you're here, please stand up, Mark DeSmet, Kim Granger, Julie Phelps, and all of the academic committee chairs and ANet leaders. It's your work that enables us to get the program that we attend to while we are here. So thank you very much. I would like to call Tammy Marshall to the stage. There she is. Hasn't she done an outstanding job? So I'd like to thank Tammy for all of the work, and this would be on behalf of AMATYC, and this is to recognize your work for the 2017 AMATYC Conference in San Diego. So thank you. Outstanding contributions to math at the two-year college level. So thank you so much. Thank you. It's time for our breakfast speaker. I was fortunate to be able to sit at the table with Jim Matthews. I have known Jim for a number of years. He is a professor of mathematics and computer science at Siena College in Loudonville, New York. I don't remember when I first met Jim or heard him speak, but I do know that he has a knack for mesmerizing his audience with the problems he chooses to discuss during his presentation. I wonder what problem he was discussing when he was dressed as a pirate standing on top of desks. Maybe he'll share that with us. He did a video trailer for us, and it's on the AMATYC Facebook page. Only Jim would leave us with a cliffhanger. He says that he will be talking about the most astonishing problem that you'll ever see. He wouldn't say what the problem was, and he encouraged us to come to the session today to find out if he was exaggerating or not. He said that he will let the mathematics do the talking. He's shaking his head for those of you who can't see that. So it's been nearly 2 months since that trailer was posted. I am excited to find out what that most astonishing problem is. The title of Jim's talk today is Key Components for Any Math Course: Newspapers, Trains, and Lockers. I am sure that you all are going to enjoy his presentation as much as I have enjoyed the ones he has given in the past. Please join me in welcoming Jim Matthews.
Thanks. Thanks, Jane. Do you have the clicker?
Yes.
Good morning. Thank you, Jane, for having me here, and Kevin and Beverly for taking care of some of the details. This morning, for a talk like this, you want to try to raise some issues that you get people to think about, some serious things, but not too serious because it's a breakfast. It could be a real downer if you start the conference or end the conference with this. You can do real downers at the first one and on Thursday. And then you want to recover by Saturday and Sunday, right, when you go back. So Jane did give something away here, and I guess I did put it in the trailer. It's the most astonishing problem. So hopefully we're not setting the expectation too high and then fizzling out altogether. So I'll do my best to keep that going. So check this out. Scott did something on Thursday. I wasn't here. I flew in yesterday. And Scott did something about 1957. And I was thinking that when some of the first times I ever got a chance to do a keynote type of thing or a banquet or a breakfast talk, we actually used to do them on overhead projectors. And you think about the technology. Like, how did you display an overhead projector? And then one time I was getting a talk ready. This is like in the 90s. It must have been in the 90s. And I have 3 kids. The 2 daughters are the toughest on me. And I'm getting this talk, and I said, should I try this newfangled thing called PowerPoint? And they said, with all the disdain that teenage daughters can muster for a father sometimes, they said, Dad, an overhead is really old. You got to use this thing, PowerPoint. It's pretty amazing. So I want to just, I've used this the whole time. Look at that. Did you see that? It flips in. My daughters did this for me like 20 years ago, and I still keep it. I just keep changing the title. It flips in. It's like so cool. And whoa, look at that, another one. That's all the flipping, though. I only have 2 flips. Okay, so one of your jobs this morning is going to be to guess. Okay, so the outline for the talk. Okay, so I tried to get to some tables early. You were talking about 5 reasons to teach or to learn mathematics, and that's the serious part that hopefully you will continue that conversation here in the rest of the day. And then I'm going to back up especially one of those with 3 examples. And my table was talking about this. There are 5 reasons to teach. And actually, it was Jane. I said, I got to go put this in the slides, Jane. So I actually got this in. Jane was saying, like, oh, I teach because I want to inspire my students. I want them to love mathematics as much as I do. So I was able to clip this in, Jane. Check this out. I was working, I've been working for a bunch of years with a local elementary school and these 4th graders. And at the end of the year, they sent messages. So I don't know if you can see it. You rock, Mr. Matthews. But the important part is underneath. It's in yellow. It's hard to see. Can you see it? Math is so loving. Jane, you nailed it, the very first one. So, and then other people at my table said it's useful. And that's an easy one to convince students of, right? Mathematics is useful. Just show them some pictures like this. Look at this. What did you guys say? Jim, I think you said, like this space program and planes and stuff. That's a beautiful bridge, isn't it? I think that's in France. So obviously it's useful. And then John at my table, what did you say, John? You said it helps develop critical. This is exactly what he said. It helps develop critical thinking and problem-solving abilities. Oh, wrong picture. How'd that one get in there? I was looking for the thinker. Did you see that? Okay. So yeah. So John, there's yours, right? I couldn't get John to pose like that. Okay. And then other people at my table, David, I think you nailed this one, didn't you? It's necessary. It's needed for responsible citizenship. Like they're talking about right now, cutting taxes, increasing the debt, $1.5 trillion over the next number of years. This is the last one that grows. Okay. So, but they're talking about these tax cuts, but then they're talking about they need to offset them because they don't want the debt to grow. So they're going to drill in a national wildlife refuge, and they're going to be able to save about $1 billion over 10 years. So now you got to start thinking about what does this mean? This is why we have to teach mathematics, so we have an educated citizenry to maintain some kind of a reasonable democracy. Because if you talk about $1 billion over 10 years, well, there's how many people in the United States? 330 million approximately. So $1 billion in savings is like a Starbucks. It's not even a Starbucks cup of coffee each. So just start thinking about, you need to be able to estimate, you need to be able to do things with ratios and proportions, just be able to read the front page of the New York Times or Time Magazine, or follow the news and be able to vote responsibly, be able to talk about what we're going through. This is a really important one. Anybody in here also teach science with their mathematics? That's some people, right? Clearly, we use mathematics to help us understand the world and universe that we live in. And I have some real math examples of that coming up. But the most important reason that we teach or learn mathematics, it's the most beautiful thing that human beings do. And here's the shame, is that I do a lot of work K-12. The course that I'm teaching right now, people say, who are you teaching? I was like 14th graders, right? And so but we're all, for the most part, we're very lucky. I mean, we do have evening programs and people returning, but we teach young people. And the thing that I'm really concerned about is how many kids go through school, 12 years of math a lot of times, 10, 11, 12 years of math, and they never see any beautiful mathematics, or they never experience any beautiful mathematics. And I said, mathematics is the most beautiful thing that human beings do. It's like, if they don't see that, it's like, imagine somebody going through life and never hearing a beautiful piece of music. That's how sad it is if they don't see the beautiful mathematics. So I'm going to let you continue to hopefully discuss these 5 reasons, or your 5 reasons. In the commercial that Kevin had me do, I said there's 5 reasons to teach or learn mathematics. And maybe there's more, maybe there's less, maybe yours are a little bit different. But I think every once in a while it's good for us as educators to step back and look at the big picture. We get bogged down in a lot of the nitty-gritty of 180 school days for a pre-college level teacher, and getting through all the material in our semester. And we need to step back and say, why do we teach this stuff? So I'll let that keep going. So I'm going to give you 3, I said, serious things to think about, and then 3 examples in the short amount of time I have to speak here. And I'm going to start with a couple of Jeopardy warm-ups just to get you going. And remember, I said your job is to guess. Okay? Oh, and then the other thing about my slides, by the way, I showed you what my daughters taught me about, like flipping in, which is so cool. I have really ugly background, just solid colors. So I'm drawing attention to this because it might help some of you like it helps me. Might help some of you like it helps me. It helps me keep track of what problem I'm on. Like the background color changes when I change the color. Okay, so here are the Jeopardy warm-ups. How many state capitals are west of the beautiful city of San Diego? Tammy made me do this one. West of San Diego and east of the international date line. And actually, it depends because it's a globe. I know you could say all of them or not. You know, like, think about it the normal way, will you, math people? Like we're here in San Diego. If you went westward here, before you reach the international date line, how many state capitals will you see? Okay? Okay. Okay, you ready? Ready? Here you go. You're guessing. You're not going to lose your job if you get it wrong. Don't worry. 0. Anybody guess 0? 0. No, any guesses for 1? Guesses for 2? 2, 3? 3s, 4? It's hard to see with those lights. 4. Whoa, we got 4s. 5? Whoa. Okay, you ready? Lines of longitude. Here is Honolulu. Juneau, Alaska. Salem, Oregon. Olympia. Sacramento. Carson City. Anybody here from Idaho? I wish they would move Boise just like another 20 miles to the west. We have 7. Boise's almost west of it. There you go. Okay, we got to keep moving. I got to go faster. Suppose you get in a plane in New York City, you fly 8,000 kilometers due south, you then parachute out. Oh, wait a second. I did it in kilometers. Let's. Yeah, how are you guys doing teaching the metric system anyway? I know. We're inching along. So suppose you get in the plane, you you're in New York City, you fly 5,000 miles due south, you parachute out. What body of water are you most likely to land in? Now, I'm going to give you some choices here. The Hudson, the Gulf of Mexico, the Amazon River, the Pacific Ocean, the Indian Ocean, and the Atlantic Ocean. Go ahead, talk to your tables. I'll give you 20 seconds. Okay, so I like this. It's about, well, in a second we're going to assume that the Earth is a perfect sphere. But the length of the equator is about 25,000 miles. That means from pole to pole it's about 12,500 miles. So that means from a pole to the equator is about 6,200 miles. So that gives you a frame of reference. Okay, so what's 5,000 miles going to do from New York City? Bang. There's your answer. You are going to end up in the Pacific Ocean off the coast of Chile. In fact, almost all of South America is east of New York City. There's just a little sliver of South America that is not east of New York City. Okay, so that gets us to the first real problem. So now we've got 3 real problems coming up. This one, the background is this nice pink color. So you remember the title of this talk was like trains, included trains, newspapers, and lockers. And they ask you for it months and months in advance, and you write that down. And then you're like, I'm gathering ideas. I don't know about you. I'm putting ideas in a folder. And then you have to really put this thing together. And I said, you know, I don't want to do the train problem. Now what am I going to do? Like, I did a commercial for Kevin, and it's in the literature, the title, and I don't want to do the train problem because I think that this one actually, it's the idea for this the moral of the story for the train problem is the same as this one for the cable around the Earth. But I wanted to do the cable around the Earth, and besides, wasn't that a nice segue going from the off the coast of Chile into I can use the same picture, but. So normally there's a cable going around the Earth, but we're going to change it. We're going to make a train going around the Earth. So we're staying true to the title, and so we need a train track going around the equator. So now we are going to assume that the Earth is a perfect sphere with an equator of exactly 25,000 miles, and we have this 25,000-mile train track wrapped tightly around the equator. You got the picture? Well, there it is. So look. Okay. So the problem though is that we put in an extra 50 foot of train track, an extra 50 feet of track, and we want to raise the track off of the equator an equidistant all the way around the equator. So we're going to need trestles. And so now here's the question: how tall do the trestles need to be to take up the 50 feet of slack that we now have? And it turns out that's the statement of the problem. So we're looking at a picture something like this, and the yellow is the train track now on the Earth, and the train track, if you take up the 50 feet at just one point, you'll go up 25 feet in the air and come back down 25 feet. Am I getting feedback, guys? I'm okay? Okay. You go up 25 feet, you come back 25 feet, and then you loop tightly around, right? But we're going to spread that 50 feet all the way around the equator. How high do the trestles need to be? I just want you to guess. Will they be as high as this telephone pole? Raise your hand if you think they'll be as high as this telephone pole. Good. That's good. Because it takes up at one point, it's going to go up 25 feet and down 25 feet, and maybe you don't know, but telephone poles are at least 30 feet high. Okay. Will we be able to slide this algebra book in between the track and the equator? How many people think that book is going to fit? You think it is? A few people do. How many people think I'll be able to slide this laminated piece of paper underneath? Okay. So remember, one of the reasons that we learn mathematics, reason number 4, is that it helps us understand the world and universe that we live in. Okay, so here we go. So this is good. This is very therapeutic for me, to be in a group of math teachers. My family always asks, where are you going? I'm going to a math conference. You always go to math conferences. What do you do there? I'm with my folks. We talk about math, and we talk about teaching math. What could be better, right? So, okay. So here we go. You guessed. Circumference is 2 pi r, or the radius is circumference divided by 2 pi. So the trestle height, you see the trestle height's going to be the difference in the radii. So what we really want is the difference in the radii. Okay, so now we're going to use the radii is equal to the circumference divided by 2 pi. So we have the circumference of the track over 2 pi minus the circumference of the Earth over 2 pi. And we can put it over, it's got a common denominator. And now we plug in, because we know that the circumference of the train track is 25,000 miles plus 50 feet, and the circumference of the equator is 25,000 miles plus 50 feet, and then the circumference of the Earth is 25,000 miles. So we got 25,000 miles minus 25,000 miles, so they cancel. So we're left with 50 feet over 2 pi, which is about 8 feet. The trestles you'll be able to walk under the trestles. I forgot to say this. Has anybody seen this problem before? A few people? It's good. So, if you've seen any of the 3 problems, you just fake it, play along, right? Okay. So, because that's pretty surprising. Let's do it around an orange. Now, it doesn't make it, I know, some of you are I actually practiced this for timing with a few people. One of my colleagues said, I just don't get a train track going around the orange. I said, Marianne, it was really a cable around the orange, but I needed to keep it the train track because of the title. Okay, so imagine the train tracks going around the orange. So we got the same deal. So we go through the same thing, And look what's going to happen. The circumference of the orange is 10 inches. The 10 inches are going to cancel. We're still going to get 50 feet over 2 pi. So the train's not going to be 8 feet off of the orange also. And if you had, like, if the universe was a perfect sphere, and you had a train track going around it, and you spliced in an extra 50 feet of track and made it an equidistant off of the universe, it would still be 8 feet off of the whole universe. And the reason I substituted this for the other problem was because how many people in here have ever taught calculus? Yeah, so I figured it was a heavy calculus group. And here's the fun part. You know that the radius is equal to the circumference over 2 pi. So the change in the radius with respect to the change in the circumference is a constant. It doesn't matter what circumference you start on. The thing is a constant. Isn't that cool? Yeah. I found this problem almost 40 years ago. Actually, it was over 40 years ago in a book by Lillian Lieber, who was actually the head of the math department at Long Island University, and her husband, Yu, was the head of the fine arts department. Just think about this. This book was written in, I think I have it here, 1942. They're the author of Mitz, Wits, and Logic, and also The Education of T.C. Mitz. Ooh, let me go back. And this problem was in there, and a couple of others. This book was published in 1942. So it does make me wonder, how many women do you think were heading math departments in colleges and universities in the United States back in 1942 when Lillian wrote this book? But it's a great little book. The Education, T.C. Mitz stands for the Celebrated Man in the Street. And it was interesting because she, the follow-up book to it was Mitz, Wits, and Logic. And I thought, here's a woman writing the book, and it's the Celebrated Man in the Street. And then the next one she wrote was Mitz, Wits, and Logic, which was Man in the Street, Woman in the Street, and Logic. And of course, she used Mitz and Wits. She didn't want to use people, person in the street, right? She didn't want her book to be the pits. Did you hear that? You didn't groan. She didn't want her book to be the pits. Okay. Okay, next problem. Next problem. Okay, the newspaper problem. Okay, so suppose you have a newspaper 1/256th of an inch thick. You're going to rip it in half 50 times. Oh, my gosh. Time out. Anybody bring a newspaper? Yes. Yeah, right there. So this is kind of sad. I actually have made a living for 40 years as a math teacher on 4 problems. And this is one of them. And like I just did this. I do this every semester. I've done it in every course I think I've ever taught, from like 7th graders, like sometimes with the elementary school kids, college people, college teachers. And you take the newspaper, which is 1/256th of an inch, and you rip it in half, and you put the 2 pieces together. And then you do this again. It's not cooperating there. Come on. There. And you put them together, and you do this 52 times. And you put the pile on the floor. And how high will the pile be? Right? Will it be as high as that algebra book? Yes. Will it be as tall as Shaquille O'Neal? I love that picture. Will it be as high as the Empire State Building? See, you guys know, right? But I'm telling you, I just did this with like math and computer science majors in my discrete math class, and they're giving up when it gets like over our heads, or like I have a couple of them hanging in, and like, is it as tall as the building that we're in? And they're quitting. And these are guys who have had calculus. They are, usually sophomores, some juniors. They've had a lot of mathematics, and they still don't really understand exponential growth in their guts. And will it be as high as the moon? They laugh, let's figure this out. And if you do this on a calculator, this is not the way to do this. You punch it into a calculator, right? 1/256 times 2 to the 52nd, and you get some number in scientific notation, and they go, no, who cares? This calculator would actually be better, because at least they'd have to do times 2 times 2 times 2 times 2 times 2 times 2 times 2. But even better is when you do it on the board. And I don't have a board here. I feel kind of naked without the board. But so you have 0 rips. You have 1 piece, 1 rip, 2 pieces. And we get to the 8th rip. We have 256 pieces of paper, so the pile is 1 inch high. So now it's 1 inch high, and I take it, and I rip it in half again, and I put it together, and how high is it? 2 inches high, right? 2 inches high, and then 4, and then 8, and then 16, and then 32, and then 64, 128, 256, 5, 12, 1,024, 2,048, 4,096, 8,192, 16,384, 32,768, and this is the good one, 65,536 inches tall. And you know, everybody knows there's 5,280 feet in a mile. They know that there's 1,780 yards in a mile. And there's 63,360 inches in a mile. So at this point, at the 24th rip, the pile is more than a mile high. So now it's more than 2 miles high, 4, 8, 16, 32, 64, 128. So when you're doing this on the board, it's really good. They think you're a real nut. Can you imagine? My students actually think I'm a lunatic. Okay. Oh, there's a good one. Can we go back one? Yep. So at the 42nd rip, we've now gone out past the moon. Out past the moon. And then we keep going, though. We're out past 1,000,000 miles. There's all kinds of fun things you can do with the law of exponents and everything like this. But at the 51st rip, we're out past the sun. But you can't say how high will it be after 51 rips, because 51 is not as good a number as 52. I don't know why, but it's not for this one. But anyway, the good thing about when you go out past the sun, then you can tell them when you go home and do this experiment on your own, make sure you do it at night so your pile doesn't burn up. Okay. Okay. So that, again, just going back, one of the reasons that we teach and learn mathematics is that it helps us understand the world and universe that we live in, and because a lot of times it's very counterintuitive. Who would think that the pile of paper, that exponential growth would get you out past the sun after 51 rips? So that is an important reason for us to teach it. This is the problem. I had some warm-up problems. Did you guys do these at your breakfast table? You were just sitting there yakking, like, come on. Okay, so here are the answers. And this is going to come in handy in the third problem, the third example, the locker problem. So the natural log of 2 is about 0.693. It's true that 43 over 8 is equal to 6 minus 5/8. We usually don't do that. In fact, I do this for my students for this problem, and they're like freaking out. No, it's 5. They're like, no, I can even do 4. Like it's 4 and what, 11/8? It's 4 and 11/8, or it's 6 and negative 5/8, or okay, so we got that. And the reason I do B is because for this one, C, when you take n plus 1 and divide it by, I don't have a board, and I'm not going to do it, but if you do the synthetic type division, if you overestimate 2, then you have to subtract 1 over n over 2 plus 1. Okay? And then the limit problem, the answer was 2. It's like the limit is n goes to infinity on that. And then 7 factorial is equal to 5,040, and I don't even remember what the question was, but that's okay. We'll get to it. Back, what was that last one? What was the last question? So suppose that you have a locker room. Suppose you have a locker room with 20 lockers, numbered 1 through 20. And you have a team with 20 players, and they wear jerseys 1 through 20. So you have players 1 through 20 wearing jerseys 1 through 20, and they have lockers 1 through 20. And player 1, the jerseys, the players' jerseys are randomly distributed into the lockers, 1 jersey per locker. Okay, so you've got 20 jerseys in the lockers. Every locker has exactly 1 jersey. And you let player 1 into the locker room, and player 1 can open any 10 lockers. What's the probability that player 1 is going to find jersey 1? It's not a trick question. It's a half. The answer's there. The answer's there. Okay. So it's 10 out of 20. Player 1 has a 50-50 chance, right? Okay, so now we're going to set this up. We got the team. We got the players wearing jerseys 1, 2, 3, and so on. They're placed into the lockers. This is one of the things that I do in my classroom with this problem. I made 20 lockers. It's not easy to carry 20 actual metal lockers around the building. And actually when I first did this, I was like, I went down to the basement. I got these sheets of cardboard, and I got some manila folders, and it was the drabbiest, boringest looking thing going. So I had some old Christmas paper, so I wrapped the cardboard, and then I stopped the staples, and I got bright yellow folders, and what a difference it made. It's weird. Okay, so player 1 enters, opens 10 lockers. Probability that she finds her jersey is 1/2. She goes out the back door of the locker room. She doesn't take her jersey. The jerseys are left exactly in the same lockers. The doors are all shut. So the locker room looks exactly the same for player 2 as it does for player 1. And player 2 gets to come in and open any 10 lockers. And if player 2 finds her jersey, she's successful. What's the probability that player 2 is successful? 1/2. Good. Oh, good. You guys are quick this morning. You've had your coffee. This is good. So let's see, I got to flip through some slides here. So the probability, she finds hers is a half. Player 3 does the same thing, player 4, player 5, all the way up to player 20. Okay, what's the probability? Oh, back up. The whole team is successful if and only if every single player is successful. What's the probability that the whole team is going to be successful? 1/2 to the 20th, right. So it's going to be 1/2 to the 20th. They're all 1/2s. And 1/2 to the 20th, catch the slides up, 1/2 to the 20th is actually a little worse than 1 in a million, right? Okay. Suppose that, well, not suppose, the players are allowed to talk before they start this game. They're allowed to talk before they start the game, but once the game starts, they cannot communicate with each other in any way. So player 1 has to go in, does her search, goes out the back door, then player 2, they can't communicate with each other. Can they improve their odds of winning the game, of being successful, to something better than 1 in a million? Yes, if it wasn't, this would be a bad example to use for this talk, because I only have 30 minutes. I can't afford to put in a problem that doesn't go anywhere. That's good to do sometimes, but I can't do it. Okay, so at your tables, quick, you get 60 seconds. Come up with a strategy that will improve their odds. Okay, so we don't have enough time, and you're too big. I don't give you much time, obviously, and I'm going to tell you where I got this problem from at the end, but I've done this like for a talk like this, and one of my favorites, I got to do it at Brooklyn Technical High School in the library with like 150 Brooklyn Tech kids. That's a really large high school. It has like over 8,000 kids in it. It's 10 stories high. Somebody said, "Where is it?" I said, "In Brooklyn." And, you know, it's like, so there was one girl who came up with a really interesting way that I'll tell you about. But when kids get stuck on this, sometimes they do, I say, well, what's the team's probability of success? Actually, this is a good question just to see if they're thinking. What's the team's probability of success if nobody opens locker 17? 0. So that, just giving them that question and making them think about that sometimes gets them to think, oh, I need to make sure every locker is opened. And then you say, well, what happens if locker 17 is only opened once? Oh, that might not be so good either. So they start thinking, I want every locker to be open about the same number of times. And then some people, this is like one of the most frequent things then is people say, let's have the odd players open the odd lockers and the even players open the even lockers. Did some of you do that? Any even odders here? And then some people get more intricate and they say, let's have player 1 open lockers 1 through 10. And player 2 open lockers 2 through 11. And player 3 open lockers 3 through 12. And player 10 open 10 through 19. And 11 opens 11 through 20. And then 12 opens 12 through 20 and number 1, right? And then it turns out that all of those methods, what's going to happen is every locker will be open 10 times, exactly 10 times. And all of those are isomorphic to the first 10 players picking the first 10 lockers and the last 10 players picking the last 10 lockers, right? So now the question is, will this help? Because think about this. the only way the team can win is if jerseys 1 through 10 are in lockers 1 through 10, and jerseys 11 through 20 are in lockers 11 through 20, and what's the probability of that, right? Well, we're going to figure that out. So that is the probability is what we need to figure out that probability. We need to know how many ways the lockers can be distributed, how many ways the shirts can be distributed into the lockers, and how many ways can you randomly distribute the 20 shirts into the 20 lockers. How many ways can you put the, that's incorrect for the question, how many ways can you put the shirts randomly distribute the shirts into the lockers? 20 factorial, right? 20 factorial ways the shirts can go in the lockers, right? And then the only way the team can be successful is if the smallest 10 jerseys are in the first 10 lockers. And how many ways can you do that? 10 factorial. And then for each one of those ways, there's 10 factorial ways that the jerseys 11 through 20 could be in the last 10 lockers. So I was checking this out. Somewhere in transport, the slides got messed up. I wanted to pop those numbers up one at a time. But it's 10 factorial times 10 factorial over 20 factorial. Did you guys compute that? You didn't compute that? That's 1 out of 184,756. Yes. Good number to know. Because it's 20 choose 10, actually, the denominator. OK, so hey, think about that. We just improved the team's chances of winning by a factor of between 5 and 6. Anybody do anything else? This is where this girl at Brooklyn Tech said, how about, and actually the way I get this to work in my class, and it's amazing, is I have one person go up to those boards, and that person doesn't know what they're going to do. But the rest of the class, I say, what could that person do? Imagine you got person 1 standing there in front of 20 lockers. What should person 1 do? Open locker 1, right? And they open locker 1 and they see jersey 5. Dang. What do? They go to locker 5 and they keep following the cycle that they're on, right? So check this out. So here's a player. She's player number 3. So she opens locker 3 and she finds jersey 2. So then she goes to locker 2 and she opens locker 2 and she finds jersey number 5. And then she goes to locker 5 and she opens locker 5 and she sees jersey 1. And then she goes to locker 1 and she opens locker 1 and she finds her jersey. Now, it doesn't matter what the first player does. Player 1 is going to have a 50-50 chance of success no matter what scheme you come up with. So we have the best we can do is a probability of 1/2 for the team. And it's not going to be that good. But what's interesting is that if player 1, or in this case, if player 3 is successful, every single player on player 3's cycle is going to be successful. And I don't have time to convince you of that, but that's one thing that you have to think about. And that's definitely true. Maybe we could do it, right? Player 2 would go in and open locker 2 and get a 5, and that would send them to locker 5. And that would see a 1, and that would send them to 3, and then to locker 1, and they see a 3, and they go to locker 3, and it sees a 2. Every player on that cycle is going to be successful. So that is really cool. And that's the big idea here. So that means that the team will be successful as long as there is not a cycle of length greater than 10. And this is really good for you probability stats people. You don't have to worry about the inclusion-exclusion principle. Because if you have a cycle of length 11, can you have 2 cycles of length 11? No, the next longest cycle you could have is a 9. If you have an 11, the next largest cycle you can get is a 9. So you can only have 1 cycle of length 11 or 1 cycle of length 12. So we don't have to worry about the overlap deal, which is really nice for the analysis here. So the probability of the team being successful is 1 minus its probability of failure. And the probability of failure is basically the probability that you have a cycle of length 11 or a cycle of length 12 or a cycle of length 13 or a cycle of length 20. You with me? I think you are, but that was good. Just nod, you can just, if you don't want to say anything, just nod your heads. I can kind of see it through the glaring lights there. OK, so we just have to figure out the probability of those cycle lengths, right? Well, check this out. The probability of a cycle of length 11, probability of cycle of length 11. We need to pick 11 numbers that are going to be on the cycle. How many ways can we pick 11 numbers that can be on the cycle? 20 choose 11. So 20 choose 11. Now, how many ways can we put them in a cycle? This was the warm-up question. That was the warm-up question. How many ways can I put 8 numbers on a clock face? Right? And it was 7 factorial. Like if I put them in a straight line, it would be 8 factorial, but once you put them in a circle, it's 7 factorial. So the number of ways that you can put 11 numbers in a cycle is 10 factorial. And then you have 9 other numbers that have to go in the lockers, and we don't care which 9 they go in. Right? I don't care if I have 9 cycles of length 1 or I have 1 cycle of length 9. It's not going to matter. I'm going to have small cycles. So that means that the probability of a cycle of length 11 is 20 choose 11 times 10 factorial times 9 factorial over 20 factorial. And amazingly, that comes out, do the arithmetic, that comes out to be 1/11. That's really cool arithmetic. And so guess what the probability of a cycle of length 12 is? 1/12. You guys are good. And so on. Woo! So I need 1 minus, did you see that? Dang. Shoot, I overshot. So okay, I was going to say, do this at your seats. There's got to be some really geeks who come to breakfast with their calculators. So you add up the 1/11 plus the 1/12 plus the 1/13 and so on, and you're going to get like 0.66 something. And so the probability of success is 0.33 or 33, approximately 33%. And now you be the judge, but I've been collecting problems for over 40 years. And this is maybe one of the most beautiful, astonishing things I have ever seen, that we have just changed our odds of the team's chances of success, or odds of success, from 1 in a million to 1 in 3. And even better, I can teach a group of 5th or 6th graders how to do it, like how to win the game. Be tough to get them to understand the analysis. But they could follow the directions. Hey, you're player 1, open locker 1. If you see jersey 5 there, go to locker 5 and keep going. Right? You can teach a group of kids to do that in just a few minutes. But we just changed the odds of winning from 1 in a million to 1 in 3. You're like, holy moly. Usually say something else. Okay. So I know what you're thinking. You're sitting there going, yeah, but what happens if there's 30 players on the team or 40 players on the team? So think about the random method with 30 players. You'd have 1/2 to the 30th, which is 1 in a billion. Or with 40 players, you would have 1/2 to the 40th, which is 1 in a trillion. Okay? But what happens when we do the linked method with them? If you do the first 15, last 15, or the first 20, last 20, you'll get a good speed up, like 5, 6 times better. But why would we do that? We have the linked method. So what will happen with the linked method is, first of all, we need our n to be even, because like if you have 35 players, how many do they open? 17 or 18? 17.5, right? So n is even. And so what we need to do is we basically need to add up. Like you remember we added up the 1/11 plus the 1/12 plus the 1/13. Or if we had 30 players, we'd be adding up 1/16 plus 1/17 up to 1/30. And so if you have n players, you're basically adding up 1 over n over 2 plus 1 up to, so n over 2 plus 1 up to n, 1 over these things, right? So you see that there. And that sum, actually, I'm taking the shortcut here for time. Usually what I do is I put that sum in between 2 integrals because I do the approximation with the integrals. I squeeze it by saying, hey, basically I'm doing rectangles, and so my sum of the rectangles is greater than the sum of the lower rectangles, and it's less than the sum of the upper rectangles, so I can connect it to a nice little calculus picture where we start to let the limit go to the width go to 0. And when you do this, though, what you get, well, look at that integral, the integral of 1 over x from n over 2 to n. We get the log, it's the log of x, right? And so you get the log of n minus the log of n over 2, which is just the log of 2, which is 0.693, which means, think about this, that means that's the probability of failure. So the probability of success is always over 30% no matter how large the n gets. So now you have problems that you can change your probability of success from 1 in a quintillion to over 30%. Or 1 in a Google to 30%. The odds are monotonically decreasing but there's a limit, and you can't get below that. And that is just astonishing. That's not my problem. I was actually on a college tour with one of those daughters I was telling you about, and it was the younger daughter who had been on college tours with her older sister. We were visiting this college, and she's like, Dad, yes, you have to go. You're bringing me, and we got to do this. But you have to, on the tours, you have to stay way at the back, and you can't ask any questions. And I was like, God, Susan, this is killing me. So we were at this college that her sister had visited. So I had been on the tour before, and now this time I have these strict rules. I can't ask questions. I can't talk to the other parents. It's like, this is terrible. I said, Susan, can I go to the library? She said, that's a good thing for you to do right now, Dad. So I go to the library, and I always check out like the math, computer science periodical section. And there was a copy of the Math Intelligencer there, which I hadn't looked at for a while. And I picked it up, and in there was the locker problem. And some of you may know, there's a really famous middle school problem called the locker problem. And I like that because if my students try to Google the locker problem, they get another one, which is good. So, there's the thing. So, whoops, let me just go back to, well, that's good. So, it's going to be in the references, but the shame was that I started reading this article, like, what's this locker problem? And this is what I came across. So I know that this was in the Math Intelligencer. I still remember this. It was in the June issue, 2006. And I have a reference sheet. And I noticed that for some reason my email address is not in the program booklet, but I think that Kevin will have them post the slides for this where the references are. You can email me. And if you just remember, like, you can email me. You can find me, Jim Matthews at Siena College. You can get my email address if you want the slides or something. So let's go through here. So there's many reasons we teach mathematics. It's useful. It develops logical thinking and problem solving. It's needed for good citizenship. It helps us understand the world and universe that we live in. And the most important reason, and I think that last problem, is just so beautiful. Like, we need to share that beauty with our students. So those are the connections between the problems. I think that they're all beautiful, and they also help us understand the world and universe in ways that our human intuition usually doesn't allow us to do it. Recommendations: avoid DDD math lessons as much as possible. You know, the DDD, I got this from my methods instructor. I don't know if any of you knew Max Sobel. But Max said, if I come out and observe you and you're going to go over the homework and teach them the next little bit and have them practice it and assign new homework, I say that's a DDD lesson, dull, deadly, and destructive. Try to be a little bit creative. That's the fun part of teaching. Construct lessons that pass the dinner table test. So like most of you are teaching college kids, but if your kids go home and have dinner with a family member or a friend or something, and they say, you know what the dinner table test is, right? I love this with adolescents. Like, you know, some of you have middle school and high school kids. How was school today? Good. What was good about it? Can they say math? Math class was really cool today. So I would just encourage all of us to keep searching for those kinds of lessons. Continue the discussion about why we teach mathematics. And then this, I've been really lucky. I got turned on to this over 40 years ago. Collect and use great problems for your courses. Here are the references I was telling you about. My friend Robin Flatlin and colleague, we did this with integrating our math and computer science classes. That's number 3. There's the reference to Lillian Lieber, and there's the Math Intelligencer there. Jane, do we have time for any questions? No? Good. You guys have other things to do. Besides, I can't hear in here. I have one more for you. One last question. Oh, they took it off. That's good. Okay.
Jim.
Jane.
You're still on. Whoa. I have a certificate of appreciation. It was fantastic.
Thanks, Jane.
That's the official AMATYC. I brought him railroad track. I'm sure he can get it in his... And he's going to laugh.
Oh, rice. Right, the rice. Some of you know the rice problem.
He does the rice problem where he brings a lot of rice, so I thought I would bring it to him in case he decided to use it.
Yeah. Jane said to me, the train problem, do I have to go get my leggings? There was another conference we were at where...
Where's Kelly?
She had to lay down and...
Where's Kelly from my college?
Lay down on the stage.
She laid down on the stage.
They modeled the train track.
I don't know where she is. Anyway, thank
Thanks,
you so
Jane.
much.
Thank you.
Great. I now invite Nancy Sattler on stage. We'll have the drawing for the complimentary discount member registration to the 2018 AMATYC Conference in Orlando. Or it could be a 3-year membership.
First of all, I would like to thank all of you. At the Delegate Assembly, I will be announcing the region who had the greatest participation and the region that had the highest dollar amount. This morning, I'm here to report that from January 1st of this year, the foundation has received, from your generosity and the generosity of other members of AMATYC, over $23,000. This morning, we're going to have a drawing for those of you who have contributed sometime this year, and the winner will receive his or her choice of a 3-year AMATYC membership or a conference registration for next year in Orlando. And the winner is Scott Peterson of Oregon State University. Thank you all, and at the Delegate Assembly, we will be announcing the other names of the winners.
I'd like to remind you that AMATYC is accepting proposals for the 2018 conference in Orlando from now and until February 1st. And how many of you are going to go to Orlando? Because I hope to see everybody there next year. Great. I would like Jim Ham to join us on stage. Nancy. It is my honor to present you with a lifetime membership to AMATYC. The work that you have done during your time spent on the board has furthered mathematics education. I thank you for your service and know that you will continue to represent AMATYC with the rollout of the new AMATYC Impact document, as well as taking an active role in the National Math Summit that's going to be held next year in Orlando. Again, thank you so much.
Jane. It has been my pleasure to work with you on the board for the last 10 years. You have served AMATYC well, first as the Vice President of the Northeast Region, then as President-elect, and now as President. I have no doubt in my mind that you will do a great job as past President in the next 2 years, and that you will find it as fulfilling as I have in the past 2 years. I would like to present you with the Past President's Medallion, and you will be joining a group of individuals who have dedicated many hours of service to the organization. Thank you, Jane. Thank you.
Jim, we have you up here for a reason. Although your term will not officially begin until January 1st, I would like to present you this presidential plaque. It reads, the American Mathematical Association of Two-Year Colleges Award of Appreciation to James Jim Ham for outstanding contributions and dedicated service to two-year college mathematics education as AMATYC President, 2018-2019. I know that you will do a great job leading AMATYC forward in the next 2 years. Congratulations.
Thanks, Dan.
You did a great job. Jim, would you like to introduce your board?
Thank you, Jane. I'm honored and humbled and thrilled to serve as president of this wonderful organization. Serving with me is the 2018-2019 Executive Board. If you would, please stand, and we'll recognize you at the end. President-elect Catherine Kate Kozak, past President Jane Tanner, Secretary Benaz Rouhani, Treasurer David Tanner, Northeast Vice President Sophia Georgiakaki, Mid-Atlantic Vice President Dan Faringer, Southeast Vice President Nancy Rivers, Midwest Vice President John Oakes, Central Vice President Rochelle Beatty, Southwest Vice President April Strom, Northwest Vice President Sarah Pauley, and West Vice President Eric Matsuoka. Thank you. With the help of hundreds of volunteer leaders, the staff, and our dedicated members, we hope to continue along the path of making AMATYC the leading voice and resource for excellence in mathematics education in the first 2 years of college. Thank you.
I invite you now to visit our exhibitors and enjoy the rest of the conference. Enjoy. Oh, one thing, I forgot to announce the attendance. You might be interested. We have 1,472 registered with 204 guests. I could just leave it because you guys can figure out the total, but I'll tell you. We have 1,676 people present at this conference. Fantastic, the best conference ever.